and welcome to the 6.5 Summit. I'm Shelley Kramer, one of the founding partners of Futurum Research, and on behalf of my team here at Futurum and the team at More Insights and Strategies, welcome. We're glad to have you. In this spotlight session, Raj Singh, the Executive Vice President of Processors for Marvell Technologies, shares with us how Marvell is driving 5G innovation with deployment-proven solutions and stack software integrations. 5G is enabling really exciting use cases across industries. We know this, right? And the technology that Marvell is deploying is a critical piece of that puzzle. This will be a fascinating conversation. Let's get to it.
Welcome to the 6.5 Summit. I'm going to talk to you about 5G networks and edge computing. My name is Raj Singh. I run the processor business here at Marvell. And as you will see, Marvell is a leader and has been for many years in both 5G and wireless communication for infrastructure throughout the world. We have marquee names like Samsung and Nokia, who we partner with to bring 5G technology to the market, and most recently Fujitsu in Japan and Facebook connectivity as well, and others that are not yet announced. We provide complete end-to-end platform solutions. We provide them in a way that enables our customers to bring this very innovative technology to the market in a robust, qualitative, and early to market methodology. We are, with the last 15 years, we've been providing products for wireless connectivity, for backhaul, for radio networks, for transport processing, for baseband, and most recently for L1 beamforming processing in radio heads as well. Today, for merchant silicon, we truly are the number one provider of silicon and software in the world. And by our last count, we've shipped over 100 million units into the marketplace, and over 2.2 billion people are now connected to networks using our technology and our software and our hardware. And this is, of course, rising. Some of the very large networks in the world, in India, in China, in Japan, in Korea, and even here in the US, are based on Marvell technology and silicon. And if you look at 5G networks, they are evolving into something quite interesting and quite complex. And we'll see later on there's a real necessity of why that evolution took place and how the market and the industry is capitalizing on that, how Marvell is playing to that and enabling the ecosystem. If you look at this diagram, what you will see is, of course, there's the traditional radio heads, 2T, 2R, 4T, 4R, but there's also now a proliferation of massive MIMO radio heads, 16T, 32T, 64T. This is driven by the need for capacity and the need for speed, where you're able to steer multiple beams of MIMO and to specific devices to increase capacity or guarantee certain qualities of service. And in the same metamorphosis of the network, we're also seeing mobile edge computing happening at the edge of the network rather than at the core, so that the very edge of the network is now more intelligent, as is the far edge of the network. And in the near edge of what used to be, conventionally in a collapsed base station, the central office type locality, you're getting not just traditional virtualized chassis-based systems, but also servers with PCI cards that were doing inline and other acceleration to provide L1 acceleration. The far edge remains the province of CUs and L2, L3, and the RICs, but in the combination of these is very exciting, because it's, for the first time in 35 to 40 years, it's changing the topology of the network. And why did this happen? Well, if you look at the diagram on top, where a traditional rack, historically, you could, maybe there's some RNCs and other control thing, but historically you had a radio tower, you had radios at 2T, 2R, maybe 4T, 4R, really interesting. And even with LTE, the connection from that to the baseband unit, either at the cell site or co-located in the central office, was an optical fiber on CPRI, so the common public radio interface, which of course was somewhat customized by each vendor with vendor extensions to match their particular needs. But at 20 megahertz at 2G2R, the combination requirement for traffic is about 7 gigabits per second plus. Now, if you were to extrapolate that to 5G, where the bandwidth is not 20 but 100, and the antennas are not 2 but potentially 32 at 8 or 16 layers, you have 300 plus gigabits per second. Now, and a single fiber would maybe handle 8 to 10. So it's problematic to have 30 of these fibers going to a single radio head. And the backhaul similarly grew from 225 to 7. Now 7 is in the range of being able, Ethernet traffic being able to manage that. But if you look at the way you solve that, the way 3GPP did definition of 5G standard, that said, aha, yes, you can have standard BBUs, and yes, there's a split 8 that lets you either use Ethernet or optical fiber on the front haul. But the smarter money is to do more of the processing in the radio head, such that a lot of the sweeps and other things that you need to throw away at the beginning reduce the amount of traffic going from the radio head to the DU. And of course, as you can see here, it went from 314 to 25. Now 25 you can handle on Ethernet all day long, and of course the mid haul is 7 and the back haul is 7 as well. These are very manageable portions. And that was the beginning of how the split thing. This is a conventional 7.2 split. ORAN came along and said, well, if that's the case, the true nirvana is to provide a defined protocol between the DU and the RU, such that vendor ABC can interoperate with of a DUs can interoperate with radios from vendor XYZ, and everything is good. And that gives flexibility, it gives choice, it increases competition and innovation, and that's all goodness. So the splits were a necessity. ORAN used the split, specifically the RU-DU interface, and codified that in a way which defined both the messaging, the protocol, the signaling, the compression, decompression mechanism, and the timing, so that things would work in a more cohesive way, which is a very good thing for the industry. Now, within Marvell, we have also adopted this. We've said, look, there's a way to do this both in conventional networks. Conventional networks aren't going away. 95% of networks deployed today are conventional networks, are either chassis-based, but there is a desire on both for geopolitical reasons and for government intervention, as well as with operators, to have more flexibility and to have a more open system, and ORAN certainly provides that. So we are now providing silicon in the radio head for the lower L1 for 5G. That's shipping silicon today for a number of our customers. We're providing the baseband, full baseband silicon, as well as upper baseband silicon and L2 processing for the digital unit, the distributed unit, and then the central unit for the upper L2, L3, and the backhaul interfaces. And now this takes care of a conventional chassis-based things. What it does not do is address what happens if you want to use COTS servers and either in the near edge or the far edge, use some form of offload. We've taken a view that yes, you can do offload, and we can do that, but the much better way of doing COTS-based server implementations, and it's a much harder way, is to have true inline processing of data. And as most of you know, with wireless, inline processing is harder, but it's much more effective because you can have more capacity. You don't have the constraints of not being able to do COM or carrier aggregation or many of the other advanced techniques that are prevalent in the industry. Because one of the things that we're very keen to do at Marvell, and we have done with our customers, is that whether you're doing ORAN or you're doing vRAN, you're doing conventional chassis-based things, or you're doing pizza boxes, you should not be losing functionality. You should not be going backwards. You should have feature parity. You should have the same performance level that you need to do this. And with that in mind, here's an example of the kinds of things we do in the radio unit, in the base station unit, in the central unit. And in each case, we have a number of different pieces of silicon and appropriate software associated with it that deals with each one of these, both for L2 control in the central unit, the connectivity. Then in the DU, we have both L2 transport, baseband processing, PHYs, we can do custom ASICs for certain of our customers, and the radio unit, massive MIMO, as well as connectivity and DFE as well. So if you go past this, what are we doing in enabling it? We partnered with our company called Analog Devices on the East Coast, which is a world leader in RF technology, to a complete RU design for a 7.2 split massive MIMO. Before this was announced, and this will now be shipping in Q3, Q4 of this year, all the massive MIMO designs that was SoC based were the province of tier ones, many of whom are our customers, but all of the ones that were in the public domain for the startups and other companies to inhabit required people to use FPGAs, which meant the boxes were much bigger, they dissipated a lot more heat, they needed different mounting mechanisms, and were more expensive. We, for the first time, in conjunction with Analog Devices, are offering a solution to the marketplace, which is licensable, that provides the SoC-based design at 32R, 100 megahertz, of course, provides the software for lower L1 beamforming, and of course, all the RF software, which Analog Devices is justly famous for. We're providing a single pizza box integrated DU, which has L1 and L2 integrated and L3 integrated, all thing, including IPsec on the back haul, and then air crypto on the front haul. All of our baseband silicon, whether it's complete baseband inline or L1, upper L1, has front haul connectivity built into the SoC, has timing built into the SOP. So ORAN compatible one has some compression, decompression built in as well. And you can see at the last one on this list is, of course, the one which says this is an inline acceleration, and I spoke about earlier, which we believe to be the way of the future. We've enabled this with a number of our customers in a way that gets them to market and gives them very high capacity in a single car, allows them to do advanced techniques, as I said, like comp and carrier aggregation, both across FTD bands and in interband and intraband, and across FTD and TDD, and as spectrum becomes more fragmented and it becomes more sparse, this becomes a very important thing for us to do. So in summary, what we've been doing over the last decade and a half is enabling large parts of the ecosystem in the wireless infrastructure space to be able to quickly and effectively go to market with solutions that are deployable, that are robust, and have 5 nines of reliability, and are at par with what customers are used to today. The innovation with 5G, of course, also is that 5G is not something that is just for devices or handsets or tablets or cell phones. It's much more than that. It has industrial components. It'll power smart cities and smart grids and vehicular traffic and communication in augmented reality, in gaming, in remote medicine. These are all very key components of a low latency, always on, very high speed network that 5G is, and has great promise to literally change the effect of society in the future. Thank you for listening. I appreciate your time.